In this video, we'll look at using the chain rule to find the derivatives of functions, and we'll also look at some other functions that we haven't looked at the rules for yet, including exponentials and trigonometric functions. So moving on to more complicated things, a lot of real-world problems regularly involve trig, exponential, logarithmic, or composed functions. We need to be able to differentiate these using their own rules. As with the rules for polynomials and their components, and also the product and quotient rules, the rules for differentiating exponentials, logs, and trig functions can be derived using the definition of the derivative. But we're not going to bother to do that because they're nicely tabulated for us right here. So the derivative of e to the x is e to the x itself, the derivative of log x is 1 on x, sine differentiates to cos, and cosine differentiates to minus sine. We can use these just to differentiate the functions themselves, or, and what's much more powerful, we can combine them and use them with rules like the product and quotient rules to differentiate much more complicated functions. Let's have a look at a couple of examples first though. First up, we've got f of x equal to 3 e to the x. This is just a constant multiple, 3, of the function e to the x. So we can combine our constant multiple rule and our new rule for the derivative of e to the x to get that f dash of x is equal to 3 e to the x, the exact same function. In b, we have f of x equal to e to the x times sine x. That's a product of two of our new functions. So we can use the product rule along with the rule that says the derivative of e to the x is e to the x and of sine x is cos x to get that f dash of x is equal to cosine of x. Sorry, we should do it in the same order. It's going to be v by du dx, so that's e to the x sine x again, plus u by the derivative of sine, which is cos x. And we can leave it like that, or if you like, you can factor the e to the x out the front. So that's how we can use these new rules. But what about when we have a function which is composed of another function, or a function of a function if you like? In this case, we can use what's called the chain rule. The chain rule says if we've got f of x equal to u of v of x, then f dash is du dv times dv dx. That's the chain rule. And that one looks a bit weird because we've mixed notations, but let's see how it works in these two examples here. In a, we've got that f of x is equal to x cubed minus x all to the power 4. Now so far with our rules except for the chain rule, we can't actually figure out the derivative of that one. Take a look now, jump back to the previous slide and look at the chain rule and see if you can identify u and v. If you can do that, see if you can go a little bit further and actually try to figure out the derivative before seeing how I do it. One way to think of these things is to talk about inner and outer functions, and sometimes that makes it easier to make sense of. It certainly does in this case. I'm going to think about the inner function as x cubed minus x, and I'm going to call that v. So I have v equal to x cubed minus x. That then means I have v to the 4 as my overall function. So I'm going to let that outer function be u, so I have v to the 4. Now remember my rule says that f dash of x is du dv multiplied by dv dx. So I have my v here and my u. Du dv is going to be 4v to the 3, and dv dx is just going to be 3x squared minus 1. Now that all looks fine, but what we really need to do to finish this off is get rid of this weird v thing. We don't want to have a derivative with respect to x still having v's in it when we didn't have v's to start off with. So let's replace v with its form there, x cubed minus x all to the power 3. We need to leave that 4 out the front, and 3x squared minus 1 left over at the end. You can expand that out if you like, but it'll take a bit of work, so I'm actually going to leave that one as it is. So that's an example of the chain rule right there. Let's have a look at this next one. So we have f of x is equal to 3 e to the x squared minus 4. Now this time you could think of it as we would normally know how to differentiate 3 e to the x, but because it's not an x, it's an x squared minus 4, there's an added function in there that's making things complicated. I'm going to let that complicating function be my v of x. So v of x is x squared minus 4. That then means that my overall function I can write as 3e to the v, and I'm going to call that u. So 3e to the v, where v is x squared minus 4. My derivative then, f dash of x, is again du dv multiplied by dv dx, that's the chain rule again. Du dv is going to be just 3e to the v, because the exponential just differentiates to give itself, and dv dx will of course be 2x. Cleaning that up, we'll get 3 by 2 is 6, e to the v, replacing v, I get e to the x squared minus 4, and I'm going to write that x out here at the front, just for convention's sake. So we end up with a derivative which is 6x e to the x squared minus 4, using the chain rule. So to finish this video off, we can now say that we can differentiate polynomials, exponentials, logs and trig functions, as well as products, quotients, and composition functions of any of a combination of those. So we've got quite a little bag of differentiation rules that we can use to differentiate all sorts of different functions and help us to solve problems in either mathematical or applied worlds.